Okay, so I'm going to cover the lecture material for Chapter 2. This is the stuff on strain. The reason I'm going to do this online, it's actually pretty simple, and I'm a little behind in the stuff we're doing in class. So I think I can just post this stuff without really losing much. The lectures are pretty one-directional anyway. I usually don't get a lot of interaction from the students back, so I think this will work okay. All right. And like I said, there isn't a lot of big concepts in this one. I'll certainly do problems in class. Okay. But of course, you're responsible for this. So even though I'm not explicitly lecturing on this in class, this still counts as lecture material. All right, the first thing I want to talk about is deformation and displacement, or versus displacement, if you will. So, if you have some body like this, and every point on this body moves the same amount, so I can draw it well, each point moves this same amount, all these points are displacing, but the body is just rigidly translating. And I think intuitively, we can appreciate that there is no strain. Because I think even though we don't have a real rigorous definition of strain, and actually this rigorous definition of strain is a little complex because it is a mathematical second-order tensor, so it's a little beyond the scope of this class, actually. But we have this notion of strain somehow measuring the deformation, not just the displacement. And what do I mean by deformation? Well, if you think about it, it's sort of how much we're locally stretching. So what you want to know is not just how does this point move, but how does this point move relative to this point, and maybe to the points around it, okay? So if you think about it, if we kind of zoom in on these 2 points, or these 3 points actually, let's imagine I can draw some sort of something like this. So here's actually 3 points. We can call this 1, 2, and 3, and they're reasonably close. They're sort of local to each other, right? They're not right on top of each other. We'll actually look at this in the limit as these vectors collapse down, but let's assume that there's some close to each other where it makes sense to talk about the deformation. Okay, now as this deforms, a couple of things can happen. One is you can actually get stretching. And if you look just at the points 1 and 2, let's say point 1 moves here and point 2 moves here. So in fact, if, where's my colored pens? Let's do a different color. If point 1 moves from here, whoops, to here, let's point 1. So this is actually the displacement of point 1. It's a vector. Point 2 moves something similar to that, but actually moves even more. So actually, here's the displacement of point 2. And if you look at this, in a sense, this line segment, I'll put little primes here to note that it's the deformed, this line segment from 1 to 2 has stretched from 1 prime to 2 prime. So there's a stretching of 1 prime, 2 prime from the undeformed configuration, which is 1, 2. Okay. Now that's one type of deformation we want to capture, and that is what we're going to talk or refer to as normal strain. That's the one that's actually associated with normal stresses. We'll have a shear strain, as you can imagine, just like we had shear stresses, but it's associated with stretching. Okay? And the mathematical definition of this normal strain, from segment 1 to 2, right, is actually, let's call this L, and I'll call this L prime, okay? It's the change in length over the original length, or L prime minus L over L. And mathematically, we actually consider the limit as L goes to 0, and you can actually get the strain at a point, and that's the derivative of the displacement field with respect to x. Okay? That's actually the strain as you take the limit. Okay? So if you look at this, we can call this the displacement, u. This vector here is the change in the displacement as we move to 2, right? And so the change, this is actually the change in length over the original length, which is the delta x. So you can see this is kind of like delta u over delta x, or this is delta x. And then if you take the limit, this becomes the partial derivative, okay? So that's basically what you get. We won't use this too much, other than we can actually get the displacement by taking, integrating the strain integrating both sides, and this will give you that the displacement is equal to the integral of the strain dx, constant, constant integration and so on and so forth. Okay, so we'll use it in that sense. But the important thing is to understand that this normal strain is the change in length over the original length. Okay, that's the big concept. So if we have some very simple problems, like a bar has some force applied to it, I don't know what it is. It has some length of 1 millimeter, and then after the load is applied, this stretches to 1.05 millimeters, let's say. We can get the normal strain. It's the change in length, which is the 1.05 millimeters, minus the 1 millimeter over the original length, 1 millimeter. Okay? Which gives me 0.05 over 1. The millimeters cancel out, so we get 0.05. Strain is dimensionless. Sometimes people will do stuff like put inch over inch, or in this case I should probably have had millimeter over millimeter. They're obviously the same units. That's just to denote that it's a strain unit. It's supposed to be mm over mm, even though it looks like something else. Okay, so they're dimensionless. Okay, and that's how you get, that's normally the way we see the normal strain problem described. It's a stretch, but you can have stretch over anything. So, and we'll show an example later on too. All right, the second modality we see here is if we go back to this picture, and let's say we consider how this line segment deforms, the line segment from 1 to 3. And now, let's just draw that, the undeformed segment right here. But let's say this line actually deforms in such a manner that it does this. Okay, so this is actually the new node 3, or new point 3. Sorry, I teach too many finite element classes. That's the displacement of point 3. Now, this is, the reason I show this is this shows another type of strain. You could also have normal stretch along this line, but the way I've also drawn this, what's going on here? Something happened, this froze. There we go, okay. If you look, there's been an angle change, okay? I'll call that angle gamma. So this is a right angle, and this material has, in fact, not only stretched, oh, this is hanging up so much. What's going on here? That's this mouse. Okay, it's not only is it could stretch, but it's got this associated angle change. So in the undeformed configuration, a little chunk of material that looks like this, in fact, now has deformed to the following. Okay? Where this angle here is gamma. Now, that type of deformation doesn't have any stretching associated with it, but there's still definitely deformation. And the deformation you can see is associated to that angle change. So it really only makes sense when you talk about it relative to another line, but that gives you this angle change gamma, and that is the shear strain. So gamma is the shear strain, and it is that angle change. That is the shear strain. All right. So if I draw it a little better, let's get its own page going. So the shearing process, let's say we initially have a block that looks like this, and a shear type of deformation is one that might look like this. So this angle here is the engineering shear strain. Okay? This is in contrast. There's another thing called the shear strain, which is the real tensorial quantity, and that turns out to be 1/2 gamma. Okay? But we won't use that often in this class. Mostly we're using gamma, all right, which is the angle change. Now, this could also shear as follows. Form a configuration like that, and obviously we could shear in another manner like this. When the block shears up like this, it's still this angle change gamma. These are actually the same shear strains, assuming the angle change is the same. Or in general, what you typically see is the following. Let's draw a little better. Nice undeformed block. Now I'm going to draw form configuration. Purposely going to not make these angles be the same. And I'm going to call this angle Phi1, and I'm going to call this angle here Phi2, all right? And I'm going to be real careful about actually the orientation of the angles. And actually we can even call this angle here, I'll call this theta. That's the included angle. And what you can see from this one, well, what is gamma here? Gamma is really the change of the deformed shape off of 90 degrees. So we can still get gamma off this. Gamma is going to be pi on 2, 90 degrees, minus theta, the way I've drawn this. Okay? Or, in other words, I can write gamma as Phi1 plus Phi2. It's the sum of those two angles that add up to give you gamma. Okay? And now, a couple things to note. One is, when we talk about shear strains, we're talking about angle changes, but they're in radians. Okay? Very important. Radians. All right? Not degrees. Okay? You have to always, right? A degree times pi over 180. Oops, 180. Gives you radians. Radians. Okay? Okay, so easy mistake. Don't do degrees. When you're finding out angle changes on your calculator and you're going to have to do like inverse tangents and so on and so forth, make sure you have it set to radians, okay? Otherwise you're going to get an incorrect answer. You give it to me in degrees, it's incorrect. All right, and the other thing to note is that when you look at this general deformation, the sign of this angle, the sense matters. So watch direction of these angles phi. What I mean by that is, in fact, if you look at the following type of deformation, where maybe this goes like this, and this goes down like this, where this angle here is maybe 1 degree, and this angle here is also 1 degree. Okay? What's gone on here? This body has done nothing but then just rigidly rotate. So this angle here, this included angle, is still 90 degrees. So in fact, the shear strain is equal to 0, okay? Because it's still 90 degrees, right? Theta is pi on 2, so this gives me 0, okay? But if you just, so in this case, theta 1 is actually negative 1 degree. So you have to be real careful about that negative because it's going in the other direction. It's going, rotating clockwise. Theta 2 is a positive 1 degree. Okay? All right? I know I'm doing this in degrees, and I said not to do it in degrees, but I think better in degrees. But you can convert this in terms of radians. And in this case, gamma would be negative 1 degree plus 1 degree. Well, and then we have to convert it so we get the pi on 180. The conversion factor doesn't really matter because you can see these actually cancel out because of the sign change, and that correctly gives you 0. Okay? So you have to be careful of that, right? This is a negative phi 1. And if likewise, if this one moves this way, that's a negative phi 2. All right? So if this were just to do another one where it's not equal to 0, so let's say here's the undeformed lines, and then it deforms to something like this. Usually these are all very small angles, but I have to exaggerate them a little bit. Let's say this is 0.001 radians, and this one is 0.0005 radians. Okay? That means the shear strain here is in fact minus 0.0005 plus 0.001. Now, why the minus here? Because this is a negative rotation. So this gives me a shear strain of 0.0005, positive. Okay? Okay. What else did I want to say about strain? All right. Maybe I should stop there because after this, I'm going to just do example problems. And I think that's enough. I don't think there's anything else I need to say about the shear strains or the normal strains. But let's just review it, okay? So again, you know, we can talk about the displacement, but really we want to get at something about the deformation of the body. So it has to do with how do points deform relative to other points near them, right? This notion of stretching and shearing. There's two types of strains, the normal strain and then the shear strain, okay? The normal strain is associated with stretching. Where's the picture there? Just to summarize. Normal strain has to do with stretching. So if here's your undeformed block, it will stretch into something like this. The other thing interesting to note So this is like L prime. This is L. And the normal strain is L prime minus L over L. The change in length over the original length. Or it's also in the limit. Change in the displacement with respect to x. Okay. The other thing to note is there's an area change associated with that, right? Or volume change, really. You should call it really volumetric. So there actually is a change in volume with that type of deformation. The other type is shearing. And this is the one. We have a body originally like this. It will deform and shear to some angles. There you go. And here's theta 1, and here's theta 2. But the shear strain is how much this included angle is changed off of 90, right? So the shear strain is pi on 2 minus theta, but you can see that that's the same as phi1 plus phi2. Okay? And again, you can remember these equations, but I'm not the big fan of memorizing equations as much as I think this is a concept. So the normal strain is the amount of stretch, change in length over length, and the shear strain is the angle change off of 90 degrees. So something that's originally 90 degrees, how much does the angle change, right? It changed to this amount theta, okay? So the change is 90 degrees minus theta. It's, whatever this angle is, minus, it's 90 degrees or pi on 2 minus that angle. Okay, that's what it is. So, I kind of said to watch the sign of these angles, but if you remember the concept, which is really the angle change off of 90 degrees, you don't even have to worry about the sense of those. Okay, it takes care of itself. All right. Okay, why don't I stop there, and then after that we can pretty much do all the problems in chapter 2.